Hello everyone, welcome to the Spintangle. Today I am here with a very important topic of microcanonical ensemble, and this will be the last lecture of microcanonical ensemble, which is based on classical ideal gas, in which we will be discussing on a very important and very interesting phenomenon called Gibbs Paradox. Okay, Gibbs Paradox. Gibbs. So before going to the Gibbs paradox, let's know what is classical ideal gas in microcanonical ensemble and its mathematics. Okay, so let's give an header: classical ideal gas. Okay, what is a classical ideal gas? Classical ideal gas means the gas obeying MB statistics, Maxwell-Boltzmann statistics. Okay, this is all. Okay, let's take a classical ideal gas. Let's take a classical ideal gas of n monoatomic non-relativistic, they are not relativistic. Okay, their velocity is quite smaller. Okay, non-relativistic, non-interacting, distinguishable, because they are Maxwell-Boltzmann statistic. They are following Maxwell-Boltzmann statistic. That means they will be called as distinguishable particles. Okay. This is an important parameter. Mark this thing, especially mark this thing. Just wait. Mark this thing. Okay, distinguishable. So distinguishable in a volume V. Say this is a classical ideal gas. Okay, in a volume V, and there are n molecules. Okay, there are n molecules which are monoatomic. So the number of particles I am writing here. Okay, so in case of microcanonical ensemble, our objective is to study the entropy first. What is entropy here? H is equals to KLN microstates. Okay, therefore this is a classical ideal gas, hence we can write the microstates for n particle. For single particle microstate, I am writing first single particle microstate will be what? Single particle microstate will be given by, say this. I have given the formula, that was HF, because this is here I think here dfq and here dfp upon hf. Okay, therefore for n particles, say you have f is for one particle. Okay, f is equals to 3 in 3 dimension in 3D. Say for one monoatomic particle, f is what? 3. Therefore for n monoatomic particles, f will be what? 3n. Therefore for n particle microstate will be what? This is the single particle microstate. Therefore the n particle microstate will be the n particle microstates will be given by omega n. That means this becomes d 3n q d 3n p upon h3n. Okay, I think that's all. Therefore from this thing you can easily write this thing as, what is this? What is here a term you have that d3n q. It will be what? It will be the volume powers n, because we know, because d3q is what? This is the spatial volume. This is the spatial volume for single particle. As this contains a power n, therefore the total volume will power n. Okay. Now the second term, I am going to the second term, that d3np. What is this? You have to know one thing, that the general formula of volume is given by the general formula. Before going to this thing, I am writing the general formula of volume. The general formula of volume is given by, for if the system is in 3 dimensions, then d will be 3. Okay, this is the dimension, d for dimension. Therefore what is this? Pi to the power d by 2 upon d by 2 factorial, here it is r to the power d. You have to remember one thing, it's in doing this thing, that you may encounter an extra term, say half factorial. What is half factorial? I think half factorial is root over pi by 2. I am not sure about this. You can check this thing. Okay, I am just writing for your understanding purpose, that you may encounter this term half factorial. Half factorial, you will be fumbling with this thing, that what is the value of half factorial. I think so that half factorial might be look like this from the concept of gamma function. Okay, so let's check this thing, the volume formula, before going to this fact. Okay, I will be going to this fact. Before going to this fact, I am doing this. Okay, therefore for 3 dimension, say for 3 dimension, the value of d will be what? 3. Therefore volume will be what? Pi to the power 3 by 2 upon 3 by 2 factorial. Just wait. 3 by 2 factorial. Here will be what? R cube. This means pi to the power 3 by 2. Here it will be 3 by 2 times 1 by 2 factorial. And here it is R cube. The value of 1 by 2 factorial is what? Pi to the power 3 by 2 is on the numerator, and here it is 3 by 2. And half factorial will be what? Pi to the power. I am writing not this thing as root over pi. I am writing this pi to the power half, so that we can cross them up. Okay, that becomes, therefore it becomes, I think, 4 by 3 pi r cube. This is the conventional volume formula for a sphere. Okay, this is the conventional volume formula for a sphere. You have to remember this thing. This is an interesting formula. I think this is an interesting formula for determining volume each and every time. Okay. So now we are going to the fact that what is the value of integration dqp dq d3 and p. I am writing this thing. Okay. What is the value? This is you are taking. This is the I am writing this thing that this is the volume in p space. Okay, this is the volume in p space. This means momentum space of a sphere. Say you have the momentum space. Okay, all the axes are here. All the axes are this is say this is px, or say this is py, say this is pz. Therefore you have a volume, you have a three dimensional. This is a part of the sphere. I am taking this is a part of the sphere. Okay, therefore it has a radius, say it has a radius which is given by p. Therefore the volume of this thing will be what? Therefore the volume I can write this volume as, therefore d3np will be what? Will be from the general formula. From the general formula we can write this thing pi to the power 3n by 2, because the dimension will be what? 3n for n particles, and in the denominator what we can write that 3n by 2 factorial, and here it will be p to the power 3n, because the radius in this case, radius in case of momentum space, what does it become? The radius becomes p. Okay, you have to remember this thing, that the radius is taken as p, because you are doing the mathematics for momentum space. Okay, I think this seems correct to me. Now let's go to the original microstate formula. What is that? Omega n. Omega n was that what? d3nq integration d3np upon h3n. Okay, this seems correct to me, and regardless of thinking anything, you have to put the value of these things. What is the value of this thing? What is the value of d3nq? The value of d3nq, I think this is v to the power n upon h to the power 3n, and the value of d3np will be what? This is pi to the power 3n by 2. In the denominator it is 3n by 2 factorial, and here it is a p to the power 3n. Okay, I think this is correct. What is the value of momentum? You may put this thing here. We know kinetic energy is given by half mv square is equals to, say, E. Kinetic energy is given by E. Therefore what we can write from this thing? We can write this thing m square v square by 2 m equals to E. This means what? In the numerator we can replace this mv as p. So p square by 2m is equals to E. Therefore p becomes root over 2me. Put this thing here. Put this thing on the formula. That becomes v to the power n by h to the power 3n pi to the power 3n by 2. Here it is 3n by 2 factorial, and it will be 2me to the power 3n. Okay, I think this is correct. what we can write from this thing, we can easily write this thing as, we can easily omit this root and by giving rise to an extra half factor on the power. Okay, therefore entropy will be what? Now I am going to the formula of entropy. Okay, I'm changing the ink. Entropy is given for n particle, entropy is given by S is equals to k ln omega n. Therefore the put the value of omega n, this is same, this is our omega n. Here it will be say is k ln here and omega n. Value of omega n is what? V to the power n pi to the, put this thing from the above formula. Okay, pi to the power 3n by 2, here it is 2me to the power 3n by 2 and h to the power 3n by 3n by 2 factorial. This is all. Now we have some easy mathematical calculations only. Therefore what we can write, k ln, here you can see this pi and this 2me has same power. Okay, so that we can merge them. Okay, this becomes 2me or 2 pi me, 2 pi me to the power 3n by 2, 3n by 2 factorial. Okay, now to write the conventional notation system, here it is a power of 3n by 2. I am giving a 3n by, I am using a 3n by 2 here in this h to the power 3n term. Okay, this means this becomes what? V to the power n. I am merging this h to the power 3n with this 2 pi me. This becomes 2 pi me by h square, because h has power 3n. To introduce in this 2 pi me, to introduce as the numerator of the denominator of the 2 pi me, we have to put this extra square term on the h. Okay, and then we will make this thing the power 3n by 2, and in the denominator it is 3n by 2 factorial. You can check this thing by pausing the video. Okay, by pausing the video you can check this thing. Now decompose this thing, what will become? K ln v to the power n plus k ln 2 pi me by h square to the power 3n by 2 minus, I think, minus k ln 3n by 2 factorial. Okay, so simplify them, this becomes nk ln v. I think so power comes in the first, nk ln v plus this power will also come in the first. Okay, so 3nk by 2 ln 2 pi me by h square minus k. What will be this thing? Remember one formula that is a important formula called, I am writing this side, writing on this side. Remember this formula is called Stirling's approximation. This is the approximated formula in case of when large number of system particles. When large number of system particles, we use Stirling's approximation. This gives us a non-polynomial type formula. This is not a long extended formula. When there is a large number of particles in a system, uh, we will be using Starling's approximation. What is the approximation? This is a mathematical formula. You can check it on Google. Okay. So what is Starling's approximation formula? This formula stands by, say, if there are n factorial times ln. Okay, this thing is, then you can write this thing as n ln n minus n. Okay, and there will be other terms. We are omitting these terms. These are the other terms that will be 0. Okay, this is called Starling's approximation. Write this thing that when there is a large number system, only this formula will be applicable. Okay, if there are smaller number of constituent particles, therefore Starling approximation will not make any effect. Okay, therefore it will become 3n by 2 factorial. This means by using Starling approximation, what we can say from this thing, that it will become, give me a bracket here, 3n by 2 ln 3n by 2 minus 3n by 2, close the bracket. Okay, this is the formula for uh, S, entropy. Okay. Therefore the simplified formula of entropy will become from this thing, say nk ln v plus, from this term and from this term you can take 3n by 2 common, 3nk by 2 common, 3nk by 2 common, and what does it become? It becomes ln 2 pi me by h square minus ln 3n by 2, and in the outside you will have only one term, 3 by 2 nk. This means what? Nk ln v plus 3 nk by 2. Here it will become the 2 ln minus, and it will goes on the denominator, and this becomes ln 4 pi me by 3n, which is, check this thing out, 3 by 2. Okay, sorry, this is 3 by 2 nk. I think this is correct. This is the formula of entropy. If you can remember this thing, please remember this thing. If but not necessarily you have to remember this thing, because this is a very big formula. You do not have to rush towards this by remembering this. Okay, this is the general formula of entropy. Just wait for a while. Okay, so this is the general formula of entropy. So what we can see, the entropy is dependent here from this formula, here on this formula. S is dependent on n and v. Okay, these are called intensive variables, because intensive variables, okay, so because there is a number of particle and volume, are dependent, these are the intrinsic variables. Intrinsic variable means if you increase, say, the number of particles by alpha, there will be a volume increment of alpha v, and also we can conclude from this thing that the entropy will also goes like this, alpha s, because no other term dependent, the entropy is only dependent on n and v here, if the energy is constant for the system. Therefore s has to be this. Okay, so let's check this thing out. In our formula, let's put So S prime will be what? Let's put this thing in the place of nk. Put alpha n k. Sorry, first writing this thing. N prime k ln v prime plus 3n prime k 2. This is the changed entropy. Okay, this is the changed entropy. Ln 4 pi me by 3n prime h square plus 3 by 2 n prime k. Okay, I think I am correct. And now put the values of n prime from this formula. What does it become? Alpha n k ln alpha v, and here it will be a 3 alpha n k by 2 ln, here it will become 2 pi me by 3 alpha n h square plus 3 by 2 alpha n k. Okay, this is the new entropy, or this is the changed entropy. Take alpha common from each terms, that will become alpha nk ln alpha v plus 3 nk by 2 ln 2 pi me by 3 alpha nh square plus 3 by 2 nk. You can easily check this thing out, that the term inside the bracket is not our conventional s, is not s. Okay, therefore what we can see from this fact, we can see that s prime is not equals to alpha s. So here is the problem, that you are increasing the number of particles by a factor of alpha, and hence the volume will automatically increase by a factor of alpha, say alpha v. Therefore, being intrinsic variable, um, or intensive variable, whatever it is, okay, size dependent variable, um, s has to entropy has to increase by a factor of alpha, but it does not. This violates the systematic law of intensive variables. Okay, this is where the problem of Gibbs was occurred. Okay, therefore, so let's start the Gibbs method. Now, starting the Gibbs method. So the formula of entropy is somewhere it is wrong. Okay, formula of entropy. In Gibbs method, Gibbs analyzed the mixing of two gases, and he suggested that there occurs a paradoxical situation. This is called the Gibbs paradox. Okay, this is called the Gibbs paradox. Let's see what is this. Mixing of two gases at same temperature. Okay, say in this box, I am taking a box. Say this is a box, and this is a partition. This is a partition. Suppose this is a partition. Here the number of particles is n1, volume is v1, and at the same temperature, therefore I am taking the temperature as T. Okay, and in this side the number of particles is n2, volume is v2, and the temperature is same. Say this is gas 1 and this is gas 2. Therefore the entropy of the system before mixing, what is the entropy? Entropy of the system before mixing, I will be removing this partition and the gas will be mixed. Okay, and before mixing, before removing the partition, what is the entropy? Entropy will be, say, the entropy of this the gas 1 and the entropy of the gas 2. Therefore the entropy of the gas 1 will be what? From the formula of entropy, what we have obtained here, that n1k ln v1 plus 3 upon 2 n1k ln 2 pi m1 kt by h square plus 3 by 2 n1k. Okay, this is the entropy of the first gas. And what is the entropy of the second gas? There will be n2 k ln v2 plus 3 by 2 n2 k ln 2 pi m2 2 pi m2. This m is what? This m is the mass. Okay, this m is the mass of the particle. From where it comes, I will be discussing on this thing. Okay, I will be discussing on this thing. Please write this thing, kt by h square plus 3 by 2 n1k. Okay, here you can see, I'll be back to this equation before going to this fact that we have the formula of entropy. We have the formula of entropy. What is entropy? Or entropy was S equals to nk ln v plus 3 by 2 nk, this k, nk ln, the formula was for 4, I think this is 4 pi m e by 3 n h square, I think this is correct, and 3 by 2 nk. This is our formula. Okay, in this formula there is an energy term, and nowhere it's been energy term either in any one in energy. This is the single energy term, so we have to remove this thing for our simplicity. Okay, for our simplicity, because this energy term is directly related to this entropy, therefore the entropy will be dependent on this energy, so we have to write this energy in terms of temperature of anything. Okay, from equipartition of energy we know that the energy of the energy, I am writing this thing, energy of n particles in 3D is given by, say, E is equals to 3 by 2 n times 3 by 2 kt. Okay, n times 3 by 2 kt. So putting this thing in, this means 3 by 2 kt is for one particle and n for there are n particles, that means the total energy will be what? N times 3 by 2 kt. And you can see this 3 by 2 kt can be written as half kt plus half kt plus half kt. This is called equipartition of energy, in which a gas molecule can have three components of energy along its 3 dimensions. Okay, these are the, this is along x direction, this is along y direction, this is along z direction. Not I am taking this a dimensional analysis. These are the independent dimensions. Okay, these independent dimensions with generalized coordinates. Okay, these are along generalized coordinates, or you can say these are along degrees of freedom. How much degrees of freedom? There will be half kt terms. Okay, if there are 2 degrees of freedom, then half kt plus half kt. If there are 3 degrees of freedom of the gas, then there will be half kt plus half kt plus half kt. Okay, this thing. Therefore put this thing on the above mentioned formula, that our entropy becomes S is equals to nk ln v plus 3 by 2 nk ln, what will be here? There will be a 4 pi m by 3n h square times 3 by 2 nk. In the place of E, put this thing. Okay, and here will be a 3 by 2 nk. Okay, yes. This is all, and from this thing we get this thing, okay. I think this is correct. Okay, just to wait for a second. Okay, now going to the fact that this is our total entropy of the system before mixing. So now after mixing, let the partition be removed. Okay, let the partition or wall partition be removed. This means if the partition are removed, partitions or the partition is removed, therefore the gas, these two gas will mix. Okay, by anyhow will mix. Okay, there will be a due to the Brownian motion of the particle, you can say it like this. Let the partition be removed, and therefore the entropy after mixing will be what? The total number of particle is now what? The total number of particle is n1 plus n2. Okay, k ln. What is the total volume now? v1 plus v2 plus 3 by 2 n1k ln. What will be the first term? 2 pi m1 kt upon h square. This is for the first gas, and for the second gas there will be another term, 3 by 2 n2k ln 2 pi m2 kt by h square, plus there will be a extra term called 3 by 2 n1 plus n2. Okay, this is the entropy after mixing. Okay, I am making a notation, say this is the entropy before, write a suffix notation. Okay, so the entropy increment will be what? So the increment of entropy, or in entropy, you can write it like this. Okay, so in increment of entropy will be what? That is, I am writing this thing as del S. Say S after, say S after minus S before. Okay, this is the entropy. So what I can write it from, this is a very big thing, not too difficult. Write the S after and write the S before. We have to these things. Okay, n1 plus n2 k ln v1 plus v2 plus 3 by 2 n1 k ln 2 pi m1 kt by h square. Write this thing carefully so that you cannot do a mistake. Okay, 3 by 2 n2k ln, this thing also 2 pi m2 kt by h square plus 3 by 2 n1 plus n2. We are the lazy people and we have to do this kind of work. So okay, so this is okay, fine. So this is the S after, and now we have to subtract this thing from the S before. Okay, so what is the S before here? n1k ln v1 minus 3 by 2 n1k ln 2 pi m1 kt by h square minus 3 by 2 n1k minus n2k ln v2 minus 3 by 2 n2k ln 2 pi m2 kt by h square minus 3 by 2 into k. I have just put this thing I have just put the s after and s before only. Okay, this is a very weak looking equation, not the too difficult one. Okay, so what does it become? There will several terms will cancel out from each other. Let's check what will cancel out. This term will cancel out with this term. This term will cancel out with this term. 3 minus 3 by 2 nk minus 3 by 1 3 by 2 n1, and this goes with this thing. Okay, am I correct to this thing? Okay, okay, that's fine. There the surviving terms will be what? Surviving terms will be n1 plus n2 k ln v1 plus v2. This is the first surviving term. The second term will be what? n1 k ln v1 minus n2 k ln v2. This thing. Okay, so what will be this? This thing is, I am writing this, decomposing this thing. Okay, what will become? n1 k ln v1 plus v2 plus n2 k ln v1 plus v2 minus n1 k ln v1 minus n2 k ln v2. So you can take n1 k, this term goes with this term, and there will be a dividing relation. This means you can take n1 k common from both. That becomes n1 k ln v1 plus v2 by v1 plus this term goes with this term. You can take n2k common from both the terms. Okay, n2k, that becomes n2k ln v1 plus v2 upon v2. That's all. You can see that this is the entropy increment. Okay, this is our entropy increment. This means that this is greater than 0. You can see this thing, this is not equals to 0. Okay, this term and this term will not looking 0. Okay, that means this term will be greater than 0. Okay, now let me write more in more simplified format, that say this is our gas chamber. Say you have a partition here, n1, v1 and t. I am not writing t. Okay, here n2, v2, because both are maintained in temperature T. If you increase number of particles in this box, there will be increment of volume, and also the same case will be in for this case. Therefore, we can easily see that number of particles increase the volume. Okay, if the walls are not too much rigid. Okay, if the walls are not too much rigid. Okay, just wait. In proportional to V. That means what? That means I can write it like this: N1 proportional to V1 and also N2 proportional to V2. That means N1 by V1 is equals to N2 by V2. That means what you can write, that N1 plus N2 by V1 plus V2. I am suffering from a microphone problem. Okay, just wait for a while. Okay, this means that I can write this thing like this, that N1 plus N2, or say V1 plus V2 by V1 will be equal to N1 plus N2 by N1, and also V1 plus V2 by V2 equals to N1 plus N2 by N2, because they are in a linear relation. Okay, they are in a linear proportionality relation. This means, now put this thing, now plug this thing on the formula instead of, in the place of V1 plus V2 by V1 and V1 plus V2 by V2. Okay, therefore the formula will be changed as, therefore del S becomes, let me change the ink, therefore del S becomes n1k ln n1 plus n2 by n1 plus n2k ln n1 plus n2 by n2. This is the formula. This is the formula in terms of number of particles. Okay. So what is this? Gibbs predicted that, I am writing this thing as Gibbs predicted that entropy of a mixing to be positive. Okay, entropy of a mixing to be positive, and as you can see, this is also positive term, there are positive terms. Okay, and as expected it is positive. Up to this thing our expression is okay to deal with. Okay, but mixing of same gas, we have taken to different gases. Okay, we have taken to different gases in the very initial of our problem. Therefore mixing of same gas, what is the mixing of same gas? Say you have a container like this, I am drawing a container, say this is our container, and in this container there is a total volume is what, V, total number of particles is what, N, and mixing of the and in the and say in this position there is a partition. Okay, if you remove this partition, therefore the gas will mix up. Okay, this is a reversible process. Why this is reversible process? Because if this is same gas, sorry, this is same gas. Okay, if this is same gas, then by putting the partition again the system will remain in the initial position. This means mixing of same gas is a reversible process. You can do it again. Okay, this means you can have the system in initial position like this, and you can go to the final position by opting out the wall, and then after putting the wall again you could go to the initial position again. This means this is a reversible process. Okay, so in a reversible process there is, in a reversible process, I am writing this thing, in a reversible process the entropy should not increase, because the system is in initial position, then goes by anyhow to the final position, and then again the system comes into its initial position. Therefore if the entropy of this thing is Si, say in this initial position, and in this position there is Sf, then the Si, then it goes to Si to Sf, and also this goes back to Si. This means no entropy should increase in this case, because the what will be the in a reversible case, I am specifying it more. Okay, say S initial is the final state entropy, initial state entropy, and Sf is the final state entropy. Therefore if you goes from this to from this and goes back to this thing again, therefore what is the final entropy? Final entropy will be this. because this process ends here and also process started from here. Therefore del S will be what? Del S will be S initial minus S initial. The entropy should be 0 in this case because you are ending the process in S initial again, in initial state again. So there should not be an increment in entropy. Okay, but what we can see from the Gibbs formula that del S is n1k ln n1 plus n2 upon n2 plus n2k ln n1 plus n2 upon, sorry, this is n1, this is n1, this is n2. This is a positive term. This is a positive term. This means del S is not equals to 0. It was predicted. I am writing this predicted for reversible process. Predicted for reversible process. But in case of reversible process also, the entropy is dependent on the number of particles. In case of reversible process or irreversible process, whatever it is, the entropy will be positive. This is called Gibbs paradox, and this creates a paradoxical situation. Okay, that a conflicting, this is a conflicting statement which looks bizarre at the moment. It is called Gibbs paradox. Okay, I'm elaborating this thing again and again. Okay, it means mixing of two gas. Say the system was initially at this point, and then the system goes to this point. Okay, this point to this point, and then again the system comes back to the initial position. Then what is your final position? Your final position is this initial position also, because you are in a reversible cycle like a system. Okay, so you have started from this thing. Here the entropy was Si, and also even after ending the process, the entropy of this thing remains the same because the system does not change its position. Okay, therefore del S will be what? Si minus Si. That should be equal to 0 for a reversible case, but that does not coming 0, that is coming to be positive. Okay, this is Gibbs paradox. It is a paradoxical conflicting situation in which the mathematical treatment does not resembles with the predicted or the theoretical statement. Okay, this is called Gibbs paradox. In the very next video, we will be discussing on the removing of Gibbs paradox. Okay, removing of Gibbs paradox, and finally we'll do some standard problems related to microcanonical ensemble, and that will be our last lecture. Okay, thank you for staying with us, and subscribe the channel. If you like these videos, then press the like button or whatever, share among your friends, and that's all. Thank you.